topic we cover is differential equations, and there's actually a whole semester class on differential equations. So a differential equation is an equation that involves the derivative and the function, possibly. In this case, just involves the derivative and time. The derivative is a function of time. And they give you an initial condition, which is at x equals 1, y equals, or t equals 1, h of t equals -4. So the first thing we do in these problems is we rewrite the derivative as a ratio of differentials. So let me turn my speaker thing out there. So what we do is we change h prime into dh dt. So you get dh dt is equal to 8t cubed plus 5. And then you multiply both sides by dt. So we get 8t cubed plus 5, the whole thing times dt, like that. So that's kind of the differential form of the original equation, which is what we're trying to figure out. What is h of t? So once you get it in the differential form, you integrate both sides of the expression, or we take the antiderivative. So we take the integral of dh, and we take the integral of 8t cubed plus 5 dt. So up to this point, this sign, the integral sign, means we take the antiderivative of each part, and we can, for right now, we're just going to break it up into two antiderivatives. Later on, we won't need to do that, but just for today. And one of the properties of taking antiderivatives is you can take the constant and you can just move that across the integral sign. You can't do that with the variable, but you can do that with constants. So then you finally do your integration. So the integral of dh is just h. So that's what we're trying to solve for. Then we get 8, the constant, times the integral of t cubed dt. You add 1 to the exponent, divide by the new exponent. And actually, and over here, 1 is t to the 0 power. So what I've done is, here I took 5 outside of the integral sign, and then I had just 1 left, but I changed that to t to the 0. That's just a special case of t to the some power. So you've got your constant, and you add 1 to the exponent, and you divide by the new exponent, and then you also add your arbitrary constant c at the end. Now later on, you'll just say the integral of 5 is 5t. The integral of any constant is just that constant times whatever the variable is, but just to show you today, it's a special case of the power rule, where the exponent is 0. And then we'll clean it up a little bit. So you get 2t to the 4th plus 5t plus c. So this is called the general solution. The general solution is the solution where we have the arbitrary constant. We haven't applied the initial condition yet. So to figure out what the arbitrary constant is, what we do is we use the initial conditions to find the arbitrary constant. So what we put, in this case, we're evaluating at x equals 1, so h of 1 is going to be -4, and to actually get h of 1, we plug 1 into the general solution. So it's 4 times 1 to the 4th plus 5 times 1 plus c, and you see that the only thing we don't know right now is c, so just do some algebra here. So we get c is equal to negative 11. And so the final answer, h as a function of t, is going to be 2t to the fourth plus 5t minus 11. And we call that the particular solution. That's the solution that doesn't have an arbitrary constant. So the general solution gives you a family of solutions. They're all they all look the same, except they just are vertically displaced from one another. By specifying the initial condition, we're able to figure out exactly which curve we are on, the particular curve that we're on. That's why it's called the particular solution. Okay, so that's, we'll do this again in chapter 6, but okay, so we're going to do one more. This is the one you kind of saw me. So it's this one right here. Same kind of deal. You, oops, wrong button. Add the page. Where's the page? Add page. There we go. So this is problem 64. It says the growth rate of growth, dp dt, of a population of bacteria is proportional to the square root of t, where p is the population size and t is the time in days. That is, dp dt equals k times the square root of t. The initial size of the population is 500, so that's our initial condition. After 1 day, the population has grown to 600. Estimate the population after 7 days. So basically what we're going to do is we're going to solve this differential equation. We're going to apply these initial conditions. Then we're going to use this additional piece of information to figure out what k is. And then once we have the arbitrary constant and the constant k, then we can have the finished equation, and then we can evaluate that equation at any value of x, or any value of t between 0 and 10. So because what it says is the rate of growth of the population of the bacteria, which is dp dt, is proportional. So when you say something's proportional, that just means it's a constant. Or you could, a lot of times, I don't know if you've ever seen this before or not, but dp dt is proportional to the square root of t. Have you ever seen that symbol before for proportional? No. Okay. I'm not surprised. So don't feel bad if you don't. So that just means that what that would mean is that it's kind of like, what would I say? 3t is proportional to t. Okay. In this case, 3t equals 3t. So actually something from physics. Well, what we could say is that the force is proportional to the mass 1 times mass 2 divided by the radius. So that means if we increase the mass 1, we increase the force. If we increase mass 2, we increase the force. If we increase the radius, we decrease the force. So this kind of gives you an idea of which direction the magnitude goes when you make certain changes. Now we know the answer is force equals g times m1 times m2 divided by r squared. So to make it equal, you'd have to figure out what this proportionality constant is. In this case of Newton's law of universal gravitation, it's g. All Newton knew was the left thing. He knew that they were proportional, but he didn't know what the proportionality constant was because he didn't know what the mass of the sun was or the mass of the earth to use that kind of thing to figure it out. And when we talk, well, actually we never talk about that. But there was a guy named Cavendish, and he was kind of like a son of a what was that? Duke of Devonshire. Yeah. So he was the son of a duke, but he wasn't going to become the duke. Only the oldest child, oldest male son, became the heir, and everybody else did other stuff. And a lot of times they got, if they were smart, their parents might say, "Well, we'll give you a stipend. We'll give you enough money to live off of, and you can do your scientific stuff because that's what you like to do." So one of his sons was interested in science, and he came up with an apparatus that allowed him to measure the force of attraction between two heavy masses. So he had a mass 1 and mass 2, and they attracted each other. But the force is so small for those smaller masses that it was very difficult to measure what that was. I'll talk about it in physics sometime. Anyway, the point is Newton didn't know what G was. Somebody else figured out what G was, and actually did a pretty decent job considering the lack of technology in those days. So what that means to this problem is when it says the rate of population growth of the bacteria is proportional to the square root of t, you put this little proportionality sign, or you can say dp dt is equal to some constant k, just like this constant g, times the square root of t. We don't know what that is right now. It's an unknown, but we can use one of these pieces of information later to figure out what that is. Just like if Newton knew the mass of the Earth, or the mass of the Sun, he probably could have figured out what G was, but he didn't know that. Okay, so this is my differential equation. So just like before, you multiply both sides by dt, and you get that. And then you integrate both sides. And I'm going to rewrite t square root of t as t to the 1/2 power. And then we integrate. So you get p of t. So that's what I'm looking for. K is a constant, so I just take that outside of the integral. You add 1 to the exponent, divide by the new exponent. That's the power rule. And you add your arbitrary constant c. So we'll just do a little algebra here to clean stuff up. So you get 2k t to the 3/2 power divided by 3 plus c. So this is my general solution. But in this case, I don't know k and I don't know c. So the first thing we're going to do is we're going to apply the initial conditions. So what that says is p of 0 equals 500. The initial side of the population is 500. Initial means t equals 0. So we could say at t equals 0, p equals 500. Okay, so p of 0 equals 500. And if we plug t equals 0 in there, you'll get 2k times 0 to the 3/2 over 3, which is all 0 plus c. So c is 500. So now we have a particular solution, but we still don't have k. Got 2k t to the 3/2 over 3 plus 500. So we've got this checked off. If we plug t equals 0 in, the answer is 500. That's my initial population. Okay. We use the next piece of information to get k. So use that p of 1 equals 600 to find k. So p of 1 is 600. And then we stick 1 in there. So you get 2k times 1 to the 3/2 divided by 3 plus 500. So now you just have to solve for k. So if you subtract 500 from both sides, you'll get this. 1 to the 3/2 power is 1. That's why they chose it, to make life easy for calculating this thing. Okay, so if we multiply by 3 and divide by 2, so you'll get 300 divided by 2 is 150. So K is 150. Okay, yeah, did that right. Okay, so now our equation is P of t equals 2 times 150 divided by 3 times t to the 3/2 plus 500. And then we can fix that out. So 2 times 150 is 300 divided by 3. You get 100 t to the 3/2 plus 500. That's P of t. So now that's my particular solution with K known, and I've combined K into the, actually K is 150, but in this final solution we multiply by 100 because of the 2/3 thing. And you can, again, P of 0 is obviously 500. If I do P of 1, just to confirm I did it right, you'd have 100 times 1 to the 3/2 plus 500, which is 100 plus 500, which equals 600. So, I did that part right. So once you have this equation, then you can use it for any part of the domain, and this second part of the question is in the domain. So all we have to do now is find P of 7. So that's just a matter of plugging 7 into the particular solution. So we just get our calculator out for that and see what it is. So 100 times 7 to the 3/2 power plus 100 plus 500, and I get 2,352. So the population after 7 years is 2,352. So that's just the math. What we do is we take dp dt and multiply both sides by dt. We integrate both sides. The integral of dp is just p. Here we take the constant out, integrate this, add 1 to the exponent, divide by the new exponent. That gives you your general solution. Then you apply your initial conditions to find your arbitrary constant c. Once we had c, then we could use the second piece of information to figure out what k is. Once we had c and k, we had the actual population as a function of time. And then we can apply it. It turns out normally bacteria doesn't grow that way. We'll find out in Chapter 6, because we can't do it until we have Chapter 5. But the differential equation for normal growth, if you looked at the rate of change of bacteria growth, it would be equal to some constant k times p. So here it's a function of t, but reality it's the rate of change of the growth of bacteria is proportional to the population size. That kind of makes sense. I mean, the more bacteria you have, the more bacteria can have cell division, and therefore that, the more you have, the more, if the number governs how fast things change, then you have this differential equation. It turns out that the solution to this, if you actually do, when we go to Chapter 6 and Chapter 5, we'll find out the population as a function of time is equal to some, we'll call it P0, some initial population times e to the kt. So it's an exponential equation. So this differential equation gives you a solution which is an exponential result. And that's why why you can get sick so quick with bacteria or viruses, is they grow at an exponential rate. So if if they keep, you remember what an exponential curve looks like. It goes. Okay. Anyway, we'll do that solution later when we know how to handle this. But this is kind of unique because here we have it as a function of t, which is the independent variable. Here it's a function of the dependent variable. But anybody who took biology last year, maybe you can appreciate that. Okay, so here's the homework assignment for section 1, chapter 4. Not a whole lot to do. So these are due next Friday. Okay, so we're moving on to section 2, which is actually, I find it interesting. And I've taught this class a couple times. Okay. So this section is kind of equivalent to what we did in chapter 2, where we used the limit definition to figure out what the derivative was. What we did is we looked at a couple of examples, and then we came up with some general rules that applied to, say, the power rule and the trig functions. We used the squeeze theorem there, looked at square roots. We used the rationalization there to help us find the limit. So what we're going to do in this section is going to find the area underneath the curve, which seems completely opposite of what we've been doing, or has no relationship to what we've been doing, but we'll find out that's basically Newton came up with this thing called the fundamental theorem of calculus, which relates what we do in section 1 with what we do in section 2. But for right now, they're kind of separate concepts. So this is just you don't have to write this down. This is just for you physics guys. If you looked at somebody hitting a ball with a bat, and you measured the force between the ball and the bat as a function of time, you would get this curve. And you would find out that area underneath the curve can help us calculate how much the velocity of the ball changes from the time it touches the bat until the time it leaves the bat. So we want to find the area underneath this curve, and we did that numerically using using the Data Studio. So how do we find the area underneath the curve? Because it is actually important. So here's a curve. So how would you estimate? How would somebody estimate the area between the red curve and the x-axis? Well, we talked about this in the first week of school, so it's not something we haven't talked about before. But one simple approximation would be to make rectangles of certain heights, and we know how to calculate the area of a rectangle. It's just the width times the height. So I'm just arbitrarily making rectangles which have they're all underneath the curve, but that's about it. Obviously, I'm going to under predict the area underneath the curve when I use these rectangles, because you've got this space between the rectangle and the curve. So the amount that I underestimated is going to be these little bits right there. But you can imagine that if I make more rectangles, then what's going to happen is these little areas are going to get smaller and smaller and smaller, and the approximation using rectangles is going to get closer to the exact solution underneath the curve. And the same is true if I draw the rectangles so they actually go above the curve. If I decide to start doing them like this, so you can see one side is based on the value of the function, And so, if I did them all above the curve like this, what I'm doing there is I'm going to overestimate the amount. So this part that sticks out is going to be more than what's under the red curve. But again, as I make the number of rectangles get larger, these areas are going to get smaller, and the approximation is going to approach the exact answer. So you can see that I've done that there, all these different ways of doing it. So I'm going to do something here. I want to look at this. I have an app. Hopefully this is working. The link's still working, so let's try that. Oh, doesn't like that. Okay. We'll find one. Okay. Area under the curve. Estimate. Estimation. Let's see if this one works or not. Enter your function. Okay, let's try that. Y equals x squared. Okay. We're going to go from 0 to 10. Let n be the number of rectangles. Let's say 10 rectangles. How does this thing work here? Okay, I got it. I just got to figure out how it actually does the calculation. How does it do the calculation? Enter the function. Enter your upper and lower bound. Okay, that's not working like I thought it was going to do, so I have to, let's see if we have another one. Used to be able to have like applets, but then when they stopped supporting it using, well, let's just put an applet and see if it says this. Applets. Okay, that's good. So we'll change that to x squared. So what you see, we have the lower bound is 0. The upper bound we can increase to something. Oh, that's the lower bound. Okay. Upper bound. We'll go to 10. Well, we'll go lower bound 0. So what they've got is 10 rectangles, and depending upon where you, whether you do the rectangles inside or outside the curve, I'm looking for a value. I don't see what the actual area is, but anyway, the bottom line is as you increase the number of rectangles, the approximation is going to approach the actual value. Okay. Now, before we can do that, we can't add things up to infinity. So we have to come up with, we have to use these equations that approximate adding stuff up. It gives us a short, an equation that allows us to add numbers or add the squares of numbers from 1 to some large value. So I'm just going to show you these equations and then we'll apply them. But before we do that, some notation. This sigma, which we've talked about in physics, but I don't think we've talked about in here, that means to add stuff up. So if I said sigma 1, 2, 3, and 4, that would say you're basically adding those numbers together. Add the numbers from 1 to 4 together, and if I add those together, I get the number 10. So that's what sigma means. So as I said, what we're going to do is we're going to do something similar to what we did for the derivative. We're going to use some definition to find the, in this case, the area instead of the slope. And we're going to work a couple of simple examples and then generalize the results that we get from these simple examples to come up with formulas and results, and then we can use those results to make the whole process a lot easier than having to do it this long way. Okay, so these are the four formulas that we're going to use. It says the summation from I equals 1 to n of some constant is equal to the constant times the number of times you add it together. And I'm going to demonstrate each one of these formulas just to show you what they mean. If we have this summation going from I equals 1 to n, and if we add I up, which is going to change, so we're going to, I will be 1, and then 2, and then 3, and then 4, and then 5. The summation of all those numbers together, the formula is n times n plus 1 over 2. If you want to sum I squared, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, instead of just adding those numbers together, you can take n times n plus 1 times 2n plus 1 all over 6. And the last one is I cubed. So if we add 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed, however many times, the addition of all those terms together is n squared times n plus 1 quantity squared over 4. So let's just look at each one of those separately. Well, the first one I didn't show here, but let me just demonstrate it. So the first equation is that the summation of c from I equals 1 to n equals c times n. So let's give an example. Let's say n equals 5 and c equals 3. So what we would do is we would, to show this representation here, we would have 3. So when this is I equals 1, and then we have I equals 2, and then we have I equals 3, and we have I equals 4, and we have I equals 5. So when I equals 1, c is just c. Okay, when I equals 2, c is c. When I equals 3, c is just the constant. When I equals 4, it's still just the constant. And when it's 5, it's the constant. And we add these things together because that's what the summation tells us to do, and that sum is 15. And what it's saying is that instead of adding these 5 numbers together, all I had to do, I could do, or instead of doing that, all I would have had to do is take c, which was 3, and multiply it by 5, which is 15. In this case, this is a little less work, but if I were adding 3 100 times, that would take a while for if I did 3 plus 3 plus 3 plus 3 plus 3. And I didn't think about, well, it's 3 times 100. So this one's kind of trivial in its result. Okay, let's go to the next one. So if you're summing from I equals 1 to n of I, and we're going to, in this case, we're going to let n equals 5. So when you say sum I from I equals 1 to 5, when I equals 1, I is 1. When I equals 2, this argument in the summation is 2. When I equals 3, the argument in the sum is 3. And so all we're doing is, this just says we're adding up the numbers from 1 to 5. We get the result. If you add those numbers together, 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, plus 5 is 15. And what it means, if you have more than 5, you just keep doing this until you get to to whatever n is. So if I did 100, I'd take 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 8 plus, just keep going. I'm going to stop there. This is to demonstrate how they got the formula. So if you think about it, if you add the first number 1 to the last number n, you get n plus 1. And if you add the second number to the next to last number, you get n minus 1 plus 2. And then if I had this number here, it would be n minus 2. So you'd add n minus 2 to 3. And you can see, though, when you simplify all these, this becomes n plus 1, this is n plus 1, this is n plus 1. So how many times do we do that? We do it half as many times as the numbers that we have. So they match up. So we have n over 2 pairs of numbers. So if n were 100, we'd have 50 pairs, and each pair adds up to 101. So that's why the equation is what it is. This would be 101. That's the summation of the first and the last, the second and the next to last, the third and the next to last. And the number of times we do that is n over 2. You don't know how, it doesn't matter. You just need to know this is the equation to use. But that's how they figure out these equations. Okay. So basically, I'm showing it here. You have n plus 1 plus n plus 1 plus n plus 1. When you simplify these, we do that n over 2 times, and so that is the equation. So if we wanted to use something other than 5, let's say n is 100. So for n equal 100, the summation from I equals 1 to 100 of I is going to be equal to 100 times 101 divided by 2, which is 100 divided by 2 times 101 is 5,050. It was a lot easier to do that calculation than it was to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus blah, blah, blah. If we wanted to do n is 100,000, if I add all the numbers from 1 to 100,000 together, what do I get to 100,000 here? I'll get 100,000 times 100,001 divided by 2, whatever that is. Okay. So that's the second formula. The third formula is this one. So just demonstrating it with an actual number, what you're doing is if n is 4, you're going to take 1 squared plus 2 squared plus 3 squared plus 4 squared. And if you do that, you get 30. And if you plug that into the equation, you get n times n plus 1 times 2n plus 1 divided by 6. So you get 4 times 5 times 9 divided by 6, which is 180 divided by 6, which is 30. So it works. Okay, that's all we're doing here is we're just demonstrating that it works. And the final one, I cubed, that's 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, which is 1 plus 8 plus 7 plus 27 plus 64, which adds up to be 100. And if we use the formula instead, we'll get 4 squared plus 5 squared divided by 4. So 4 squared is 16. 16 times 25 is 400. 400 divided by 4 is 100. So we get the same number again. So those are the equations that we're going to use in our demonstration here. And this is called. So what we're going to do is we're going to use this to define the area. So I'm going to explain. Let's just read it. It says, let f be continuous, so the function's continuous, and non-negative, which means it's above the x-axis, for a certain interval a to b. The area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is. So the area underneath the curve, what we're going to do is we're going to add up all these areas of rectangles. This is going to be the height of the rectangle. This is going to be the width of the rectangle. So that'll give you the area of the rectangle. We're going to add all those rectangles up to some value of n. So we're going to do this. We're going to use those formulas to figure out what this summation is. So then we'll have a function. Then we'll have an equation that's a function of n, and then we're going to let n go to infinity. So by doing this, we're going to find the exact area underneath the curve, not the approximate area. If n was not infinity, then it would be an approximation. But if you let n go to infinity, then you're going to have the exact area. So what's happening is we are going to have an infinite number of rectangles, but they're going to be infinitesimally thin. And in the limit, you can make that happen. Of course, you can't make them go to 0, but the limit process allows us to approach 0. The width is going to approach 0, and the number is going to approach infinity, but they're never going to equal infinity, and they're never going to equal 0. So that's the formula we're going to use to figure out the area. And we're going to use this example that y equals x squared as our demo. So I'm going to do this instead of using, just so I don't go too fast here. I tend to get carried away here. Let's just get going on this thing. So here's the axis. And here's the function. So the function is f of x equals x squared. And I want to go from 0 to 10. So that's my interval. That's what I want to do. So if this is 10, this would be 100. Obviously, it's not to scale. So when x equals 10, f of x equals 100. And I want to figure out what the area is going to be underneath that curve. And what I'm going to do is I'm going to draw a little rectangle here. And the width of the rectangle is going to be dx. And the height of the rectangle here is going to be some, and this also has some x value, right? So this is at some x value, x sub I. And then the value of the function is going to be f of x sub I. So that's the height of the rectangle. This is the width of the rectangle. So using this definition for the area is the limit as n goes to infinity of the summation from n equals 1 to I equals 1 to n of the value of the function at some value x sub I times delta x, and that's it. Now, the width of the rectangle depends upon what n is. So delta x is a function of n. And the relationship is that delta x equals b minus a divided by n, where this is a and this is b. So all we're doing there is we're saying if you take the total width that we're looking at and you break it up into n parts, each width is going to be the total width divided by the number of parts that I'm going to break it up into. So if n was 10, then delta x would be 1. We'd have a rectangle for every foot or every unit. So that's delta x in terms of n and in terms of b minus a. So for our particular case, b minus a is 10. So b minus a is equal to 10, and n is just n. Okay. So we're going to be able to use this and substitute it in there. The next thing you have to do is you have to figure out what the function is in terms of n. So the value, before you have to do that, you have to figure out what is the x value as a function of n, or a function of I, because I is going to increment. So it's going to be, it's going to be a linear relationship here, and I'm trying to remember what let's see, it's going to be 0, because we start at 0, plus I times delta x. So when I equals 0, when I equals 1, sorry, because we don't have I equals 0. We start at 1. So when I equals 1, x sub I is equal to 1 times delta x. And when I equals 2, x sub I is 2 times delta x. And when I is equal to n, x sub n is equal to n times delta x. So all we're doing is we're just incrementing the x value. For every value, we're going to start with I equals 0, which is on the left-hand side. It's actually just there. It's delta x. And then the x sub I is going to be 10 when I equals n. Because if you plug in I as n, you get n times 10 over n, and the n's cancel out, and you get 10. So this is the way of incrementing. This is the way of incrementing x in this equation. So if we did f of x sub I, that's the value of the function, that's the height of the rectangle, it's going to be equal to x sub I squared. It's going to be whatever this incremented x value is, that value squared, because that's what the value of the function is. So what we can do is we can say f of x sub I is going to be x sub I 0 plus I times delta x quantity squared, or just I squared times delta x squared. So I'll square this and I square that. Now I is not an imaginary number, it's just the counter. So then we can go back to our original area expression. The area is equal to the limit as n goes to infinity of the summation from I equals 1 to n of the value of the function, which is going to be I squared times delta x squared. So this is f of x sub I times delta x. So now we can substitute in what delta x is in terms of the number of rectangles and the width of the interval. So we're going to, so this equation becomes I squared times 10 over n squared times 10 over n. So this delta x squared is this, and delta x is that. So you get the limit as n goes to infinity of the summation from I equals 1 to n of, 10 squared is 100 times 100, you get 1,000 I squared divided by n cubed, because we get n squared here and n there. Okay, then what we can do is we can pull n. N is a fixed quantity, so it's a constant. So what you can do is you can take this constant and that constant, and you can take them outside of the summation sign. So you get the limit of this thing, and then times the summation from I equals 1 to infinity of I squared. Again, if you have a finite n, you're going to get a number. When you add all these numbers together, you're going to get an approximation to the area. But notice I have this summation from I equals 1 to, and it should have been I equals 1 to n, not to infinity. So sorry. See, I got that wrong. Let's put that to n. Where's paste? Paste. Okay, so there's the formula. So I'll just put it there. So so instead of what I did before, you're going to have this, which is n times n plus 1 times 2n plus 1 divided by 6, like that. And what will happen, and we'll do this when I get back on Tuesday, is we're going to multiply all these terms out. And it's going to, I don't want to do it too fast because we need to understand what's going on. But what will happen is there'll be terms that where n cubed, it cancels out with n cubed, and we just end up with a constant. The other terms will all go to 0. So that's kind of like when we did the derivative, that a lot of terms went to 0 except for one of them. And so the same thing is going to apply here. And it's going to end up giving me a number, a finite number as the area underneath the curve. So what we'll do is on Tuesday, we'll go back through what I just did to review it. So you kind of have your subconscious can kind of work on this and think, what the heck was he talking about? And then we'll do it slow enough so that you understand, and then we'll finish this off and we'll get the result. Okay.